After an hour of milling, the servo motor would be 100 degrees Celsius. Core prevented heat from being transferred. I added this box to duct cool air alongside the servo motor. That works really well, except the fan is really loud. Arduino integrates signals from an infrared non-contact temperature sensor, the tach from the fan, and generates a PWM signal which drives the fan. For this demo, the servo has been running for more than 30 minutes at 4,500 RPM, reaching 102 degrees Celsius before the fan controller is turned on. There is a sound that increases pitch as the servo cools. Maybe 65 degrees Celsius would be the asymptote, so 35 degrees Celsius difference from cooling. The servo has now been turned off and begins cooling to ambient, which takes a long time. The displayed runtime resets, and this may be a mistaken touch event. The runtime code is internal to the display, and an Arduino reset looks different. The fan controller reads the case temperature of the servo, which is easier to affect than the core temperature. As the fan slows, the case temperature increases because the core temperature is still hot. The fan speed then begins to oscillate despite a slowing trend, which is pretty neat. This is a Noctua Industrial 24 volt fan. It's 3000 RPM, PWM controlled, and has a tach signal. 24 volt supplies both the fan and the fan controller. And attached to the fan controller are two temperature sensors, a contact-based temperature sensor, which I started with before switching to the non-contact temperature sensor, which is IR-based, has really fast response and easier to mount. A Nextion touchscreen shows the current runtime, the current temperature, and the current fan speed, and a graph of the temperature and fan speed. Touching the fan speed changes the fan mode between maximum, minimum speed, and auto. You switch between Fahrenheit and Celsius, reset the runtime. Touching the graph resets the graph. Two 3D printed parts. There's the cover and this support, which holds the display, and an Arduino. And the Arduino is used to produce the PWM signal to control the fan, to read the tach, and to read the temperature measurements from the sensors, to read the display, and to send commands to display, update commands, that is, populate temperature and fan speed on the display. The display is programmed using a micro SD card. There's a battery holder to back up a real-time clock, and a header for GPIO. The output could potentially control the fan. It has a fast 64 kilohertz PWM signal, while the Arduino, the best it can do is 480 on most of the pins and 960 hertz on a couple of the pins. The Arduino and the display communicate with each other by 38.4 kilobaud serial, and 5 volts powers the display. The ProtoShield uses point-to-point wiring, and it's kind of a mess, but it does get the job done. There's an Adafruit bidirectional level shifter for the I2C bus. The non-contact sensor is a 3.3 volt device, and while there is 3.3 volts available to power it, the Arduino Uno's I2C bus is pulled to 5 volts. The contact sensor uses one wire serial interface, so this resistor is the pull-up for it. On the other side of the board is a Murata DC-to-DC converter that takes the 24 volts and produces 12 volts, which is fed to the Arduino. I want to describe a problem that I had with the contact sensors. This is the measurement of the resistance between the two power leads of one of the sensors. So about 0.8 mega ohms. And let's measure this one, do the same thing. About 31 ohm. 3 out of the 5 that came in the bag are working for now. A lot of heat being generated, and the Arduino was resetting. I thought at first that since the Arduino's regulator runs hot, the DC to DC converter is pretty efficient. I think it has the efficiency rating of 91%. But I had this mounted over the top of the Arduino's regulator. Moved the DC to DC converter over here to give each of them more space. So this ends up being in this empty area. And still Arduino is resetting. There was a 31 ohm resistance between ground and 5 volts, and eventually I traced that back to the contact sensor being damaged. Shown in the graph are the temperatures read from each of the sensors. And now I'm going to hold the contact sensor, and it's currently set to 9-bit precision, so it's moving in half-degree increments, but you can get a sense of how quickly it's responding. And now I'll let go of it, and after some amount of time it'll start to fall. The contact sensor has a lot of metal, and it just takes a while to warm up and cool down. The non-contact sensor, I'll just put my hand in front of it and it responds immediately. And now it took my hand away. And so it responds within a second easily to my hand's presence. At 12 bits of precision, the effective readout time is 550 milliseconds. But the smallest amount of change measurable is 0.0625 Celsius. The other times shown here are for the effective readout of the non-contact sensor. It's essentially instant, and the 20 milliseconds is the update time of the display. The non-contact sensor is a 3.3 volt I2C device, and the Arduino can supply the 3.3 volts to power it, but the Arduino Uno's I2C interface is 5 volt. Some suggest using external resistors and pulling the I2C interface to 3.3 volts, but we can dig into the Atmel datasheet to see if that's a good idea. The first thing we need to do is find which port the twin wire interface is on. So twin wire interface is what Atmel calls I2C interface, and we see that's on port C. Now we need to determine what pins are associated with the I2C interface. And pin 5 is the clock line, and pin 4 is the data line. Many of the pins on the Atmel processors have multiple purposes, and they can be programmed. That is, its function can be assigned by software. That's really neat because you could then reuse pins or use pins for different purposes. So this is the schematic of the pins that do have alternative functions. And what we're considering is if we could hook a external 3.3 volt pull-up to the pin. Now, inside the processor, there is an additional resistor, which is a pull-up resistor to the internal 5 volts. And controlling that is this FET. So we need to understand when this FET would enable this internal pull-up resistor. So working backwards, first the bubbles pop, so we can ignore this section. Next we find a multiplexer, and so the value passed to the FET is determined by this line here into the multiplexer. So this is a pull-up override enable line. So we need to understand when that will be high or when it will be low. So pull-up override enable on pins 5 and 4 of port C is set to the twin wire interface enable signal. So when we're using I2C, this is going to be high, and subsequently pull-up override enable is high. When pull-up override enable is high, then the signal passed to the FET is going to be pull-up override value. And pull-up override value is the composition of the value of the pin and the pull-up disable negated. So line over the term means negation, and PUD is pull-up override disable. So this seems like it's reasonable to, in software, disable this internal pull-up. And in fact, I did something similar for the one-wire interface when I didn't have a resistor readily available. This involved making 4 modifications in the one-wire interface library. The problem with that is once that library is updated, those changes might be overwritten, or if you make a mistake in a software, or perhaps there's a glitch on startup, there's then a chance for the 3.3 volt regulator to be connected to the 5 volt side. And granted, it's through resistors, the current is going to be low, but it just seems like a bad idea. Making a lot of assumptions that the software is going to be perfect. And in the Arduino software, their libraries, they hide a lot of the details. And when you start to do things like this, it might be better to do that in, outside of the Arduino's IDE and in the Atmel development studio. So this is the recommended solution, one of the recommended solutions for interfacing multiple voltage regions. And this example is 3.3 volts and 5 volts. And let's just consider how this works. So each side has their own pull-up resistors. And when the 3.3 volt side is driven high, then the difference between source and gate on the FETs is, there is no difference. So there's no conduction across. When the 5 volt side is high, then there's no difference, and there's no conduction across the FET either. When the 5 volt side is low, then there is conduction across the body diode of the FET. And when the 3.3 volt side is low, then the difference between source and gate is great enough that there's conduction across the FET, and it pulls the 5 volt side low. It's really very creative. And the Adafruit module, their bidirectional level converter, implements this exact circuit. This is an inexpensive device, and just removes the worry of getting the software wrong and trying to disable the internal pull-up. I want to show a little bit of the code. I'm not going to go into detail with the Arduino code. All the files are available on my GitHub repository. And if you program Arduinos regularly, or if you program C regularly, most of that will make sense. I do want to show a little bit about the Nextion programming environment, because that was new to me, and I think it'll be new to more people than Arduino coding is. Nextion has this instruction set page, and this is very terse, but I didn't find any problems with what's written here. Just the problems were in my understanding. White space for just formatting code isn't useful, and in fact sometimes I think it creates a syntax error other than new lines, and then spaces are only allowed between the function and the operands. The other resource recommended is this Nextion Arduino tutorial, and this is really good. This helped me a lot when I was not understanding the instruction set page properly. To see how someone else got this to work was really nice. The Arduino code, like I said, is pretty understandable to anyone who programs Arduinos or writes in C language. Probably the most complex part is the interaction between the Nextion, the display, and the Arduino. And that's just because of the number of cases that need to be considered. So it's not that it's complex in a theory sort of way, it's just complex in a tedious sort of way. And then after that, probably the next most interesting thing is communication with the non-contact sensor, and then updating the display with the current temperature and fan speed. This is where the programs are written that are uploaded to the display, and the graphics and the fonts are defined. The background graphic is loaded as an image file. And it needs to be the same resolution as the display that's being used, and the display type is selected when the project is created. On top of that, you can lay widgets, and the widgets are selected from this toolbox. It can be drug around. Each widget has a touch or press and release event. And remember, on the Arduino, when you press temperature or fan, it changes the units or it changes the fan mode. And that's because in the release event, the component ID is being sent back to the Arduino. So on the Arduino side, you see B0 or B1 being sent, and the Arduino knows that B0 is the temperature button and B1 is the fan button. In the case of the graph, when it's touched, the waveforms are cleared. CLV is the clear waveform function. These variables are defined, and this one is a string, and this one is a number, and the initial value can be set as well. Timers can be created, and you control how frequently the timer is triggered and if it's enabled, and you can disable it in the software. Order of operations is a little bit strange. So this is calculating the number of seconds since startup, and so RTC3 is the number of hours, and normally you'd see this multiplied by 3600, but since it's since this is evaluated left or right, 60, so you're multiplying RTC3, the hours, by 60 here, and then again by 60 here. You can do compound expressions like this, but again, they're not complex expressions, so you can't have parentheses in the logical expressions. This is a conversion of a numeric value to a text value. To update the runtime widget, which is a text widget, we assign to an attribute in that widget. For a text widget, the attribute is called txt. So we are assigning the final string to that attribute. And in this case, we're building it up by appending to the string. So you can read and write two attributes in widgets, and they are updated on the next refresh. Fonts need to be generated. They must be stored as bitmaps in the file that gets uploaded to the display. There is also a debugger. So this is the serial information that would be sent to the Arduino, and you can type in a response command to be sent to the display. So again, this is very useful. And then beyond that, beyond using the debugger here, the simulator, for debugging in hardware, you can send information to the Arduino over a serial. But what I did was put a number of extra widgets onto the display, and and then update those, put a camera on the display, record a video, come back later and review the video until I found the problem that I was looking for, and then from the values that are shown in the widgets, try to decide what likely happened. So updating a series of widgets like that would be the equivalent of a printf type of debugging style, and it's fine. There's compile, and that just checks the program syntax, and then there's this tft file out, and this is what generates the file that's written to an SD card that you slide into the display, turn the display on, and it will flash itself. If you've made it this far, thank you. You are a trooper. Did I mispronounce the display name through the whole video? Is it Nextion or Nextion? To show your support, you know what to do. Click the buttons below, and I'll see you again on the next video.